Ask anybody around you what is gravity. They probably might tell you that it's the reason why objects fall. It's the reason why Apple fell on top of Newton's head and made him think about the effects of the force. If Earth can make things fall towards it, then why doesn't Moon fall to the Earth? And why does it revolve around the Earth? Let's try to answer this question in this chapter.
Now let's try this experiment. Tie a ball to the end of the rope and start swinging it in circles. You'll probably see that as long as the ball is attached to the string, it moves in a circular fashion. As soon as you cut off the string, the ball would fly off in some direction. The force acting on the ball when the string is attached is called a centripetal force. Centripetal meaning nothing but center seeking. For a body to revolve around a circular path, this force is very important. The moon revolves around the earth and the earth revolves around the sun due to the same force. For the moon to revolve around the earth, the necessary centripetal force is provided by the earth's gravity. In our primary classes, we all have been taught that Sir Isaac Newton discovered gravity when an apple fell on him. And we also been taught that way before Newton's era, scientists knew planets revolve around the sun and the satellites revolve around the planets due to the centripetal force.
That is, gravity is the force that makes the planets revolve around the sun, and it is the same force that acts on the objects and makes it fall on the earth.
Whether is it the apple attracting the earth or the earth attracting the apple? What do you think? Or maybe both are attracting each other. Let's solve this. By Newton's third law of motion, the apple does attract the earth. But then according to the Newton's second law, force F is given by ma. Therefore, acceleration will be inversely proportional to the mass. We know that mass of the apple is negligibly small compared to the huge mass of the earth. Therefore, by this we can conclude that each and every object on the earth exerts some force on another object. Consider the two objects on the screen. The first object, which is colored blue, has mass of 100 kilos. The second object, which is also having a mass of 100 kilos, has been colored red. The separation between the two masses is 2 cm. Now observe the force. The force is 1.65849 into 10 power minus 7 Newton. Now let us double the mass of one of these substances. Let me take the red one. I'll make it 200 kilos. Now look at the change in the force exerted on the object. It's 3.31699 into 10 power minus 7 Newton. If you multiply the first value we got, 1.65849 into 2, you'll get this. That is, when you double the amount of the mass, force applied also will get doubled. Let us further increase the mass of the second object to 400 kilos and see what happens. We see that the force has increased further. So we can conclude that the force is directly proportional to the mass of the objects. We can observe the same scenario when increase the mass of the first object. Now let us increase the distance of separation between them. Let us increase the distance by 2 centimeters. What we will observe is that the force has decreased 4 times. That is the square of the distance of separation we have increased. Therefore, the gravitational force is directly proportional to the mass of the subject and inversely proportional to the square of the distance between them. We can observe the same effect when we increase the distance to 8 cm. We shall write it mathematically as F is proportional to capital M small m by d square. To remove the proportionality symbol, we need to have a proportionality constant, and that constant is denoted by capital G and is called as universal gravitational constant. and its value is 6.673 into 10 power minus 11. What will be its units? Force is Newton, distance is meter square, and weight is given in kg. Therefore, its unit is Newton meter square per kg square. Universal law of gravitation successfully explains several phenomena such as the force that binds us to the earth, the motion of moon around the earth, motion of the planets around the sun, and the tides due to moon and sun. When you drop a ball from your hand, the ball falls to the floor under the action of gravity. When objects fall to the earth under the gravitational force alone, we can say the object is under free fall. But consider this scenario. A baseball hitter hitting the ball. Is it free fall? Yes, it is. Even though the baseball hitter gives it an extra acceleration, but after he has hit it, it acts upon gravity alone. Therefore, it is also an example for free fall. In both the cases, acceleration is provided by the gravity. This acceleration due to gravity is denoted by small g. Let us derive the value of small g. Now, we know that gravitational force F is given by gmm by d square. Now, by Newton's second law, we know that F is equal to ma, where we can substitute for acceleration by acceleration due to gravity. Both them get cancelled, therefore G will be capital G m by d square. For an object near the surface of the earth, d is equal to the radius of the earth. Therefore, G is equal to gm by r square. The value of this is given as 9.8 meter per second. This G is constant for all objects near the earth. Now we have learned about the three equations of motions, which are V is equal to U plus AT, S is equal to UT plus half AT square, and V square is equal to U square plus 2AS. For free fall, we need to substitute A by G. Therefore, we get V is equal to U plus GT, S is equal to UT plus half GT square, V square is equal to U square plus 2GS.
A cheetah falls off a cliff and drops to the ground in 3 seconds. Let g be 9.8 meter per second. At what speed will it strike to the ground? What will be its average speed at 3 seconds? And what will be the height of the cliff from the ground? To answer this question, we have to know what is t. T is equal to 3 seconds. Initial velocity u is given as 0. Acceleration due to gravity g is equal to 9.8 meter per second square. Therefore, acceleration of cheetah a is equal to 9.8 meter per square. By using the laws of motion, we know that speed v is equal to u plus at, where u is equal to 0, therefore v is equal to at. So applying that, we get v is equal to 29.4 meter per second. Therefore 29.4 meter per second. Average speed is given by u plus v whole divided by 2. You know that u is equal to 0 and v is equal to 29.4 meter per second. Therefore, applying that, we get average speed is equal to 14.7 meter per second. Distance travelled. Distance travelled is given by s is equal to u plus half at square. Therefore, applying all the given data, we get distance travelled is equal to 44.1 meters. Therefore, the speed of the cheetah striking ground is equal to 29.4 meter per second square. Average speed at 3 seconds is equal to 14.7 meter per second, and height of the cliff is equal to 44.1 meter.
Mass of an object is a constant at any position in the universe. Weight depends upon acceleration due to gravity. Is mass and weight one and the same? Let's have an elaborate discussion on it. Mass is the amount of matter present in an object. It will be constant irrespective of the position of the body. Mass of a body is related to inertia. If greater the mass of the object, greater will be inertia. Now since we have understood the concept of mass, then what would be weight? Weight is nothing but measure of how strongly gravity acts upon the object. By Newton's second law of motion, force is given by mass into acceleration. By replacing that acceleration by acceleration due to gravity, we get force is equal to mass into acceleration due to gravity. This is nothing but weight. Now replace F by W. Therefore W is equal to M into G. Now what would be the SI unit of weight? Think about it. SI unit of weight is nothing but Newton. By this, we can say that weight of an object is directly proportional to the mass of the object and as well as the acceleration due to gravity. Mass of an object is constant at any point of the earth. Will the weight of an object having mass small m will be same in earth and moon? Definitely not. We shall study it. Since weight is nothing but gravitational force acting on the object, we can take weight as W is equal to Gmm by r square. Therefore, weight of an object in earth is given by We is equal to capital G capital M small m by capital R square, where capital M denotes the mass of the earth and capital R denotes the radius of the earth. The values of mass and radius of the earth are on screen. Weight of the object in moon is given by Wm is equal to capital G mm into m divided by rm square. The values of mass of the moon and radius of the moon are on screen. If we divide the weight of some object in moon divided by weight of the object on earth, we can see that mass of the object cancels out. What remains are the four terms which are constants. Adding these values, we will get it as 1 by 6. Therefore, weight of an object in moon will be 1 by 6 of the weight of the object on earth.
You might have seen a bulletin board in your school. Have you ever observed how you pin it? When you pin a bulletin board, force from your thumb is acting perpendicular to the surface of the board. Similar case is observed during hammering a nail. These kind of forces are called thrust. Thrust is a force that acts perpendicular to the surface. Now can you guess the unit of thrust? Since thrust is nothing but the force applied, SI unit of thrust is Newton. Since we have understood the concept of thrust, let's see what is pressure. When you stand on a loose gravel, you see that your feet will go deep into the sand. Now we try to lie down into the sand. Will you go just as deep? No, you won't. Now since the force exerted in both the cases is the weight of your body, then why is the depth changing? That's where the concept of pressure comes in. We know pressure is equal to force by area. If you're talking about thrust, then pressure is equal to thrust by area. If thrust is constant and area is more, then pressure is lesser. And if we reduce the area, the pressure is more. That's why in the first case, when you stand on the sand, you go deeper, and when you lie down, you don't go as much as deep.